In this video, we'll be discussing sort of the most fundamental laws that talk about how voltage and current are distributed around circuits. The first rule is Kirchhoff's voltage law, and that is a way of us trying to figure out how much voltage will go to each resistor in a different point in a circuit. It says that the total voltage changes around a closed loop in the circuit are zero. If we have some sort of circuit here, and a resistor, and a resistor, and then we're just going to come back down to the bottom just to keep it really simple, and this is 10 volts, then I don't know how big the voltage on this resistor is going to be, or how big the voltage on this resistor is going to be, but what I can say is if I went when I went through the battery, I went from, I'm going to go around a closed loop that goes like this in the circuit, around like that. I'll put voltage ups in red and voltage downs in black. So if I go up 10 volts and I want to get back down to the same spot I started from, then in V1, and I want to get back down to the ground here, V2, what I can see is that I don't know how big those individuals are, but V1 plus V2 have to be 10. We can maybe imagine this like you moving around the school. Here you are. Okay, this is the school as a whole. Okay, and basically this law is like saying if you go up however many staircases, let's say you go up here, this is going to be like the second floor, and then the third floor. I didn't really think this through. Let's put a whole nother layer on this building. There you go. However much you go up when you're going through the battery, so maybe you going up these staircases is like you going through the battery, now you're up here. If you want to get back down to this location, or back to the same spot in the closed loop, then it's unclear how you're going to do it. Maybe you could take the elevator or something, but the height you went up, h1 plus h2, has to be equal to the height you dropped. In a circuit, we view going through a battery. Usually you'll go from the negative end to the positive end as going up to a higher point of potential energy or a higher voltage, and then every time you go through a resistor, you go down a certain amount of voltage. Now the truth of this is that the wires themselves do have a small amount of resistance and do use up some of the battery's energy, but hopefully that's small enough that we're just going to basically ignore it. Kirchoff's current law, on the other hand, says that the amount of current going into a junction in a circuit is going to be equal to the amount of current coming out of a junction in a circuit. So in this case, we can see a junction in a circuit. This could be a junction in a circuit that looks like this. This is going to be similar to the measuring video here. Where this is I1, this is I2, and this is I3. But basically what we're saying is that electrons can't just build up or hang out in one spot. So the total amount in is equal to the total amount out. In this case, I1 equals I2 plus I3. Conceptually, I think this particular law is understandable if we think about it almost like cars going into an intersection. cars can't park in the middle of an intersection, so if you watch the intersection carefully and you counted the number of cars that enter the intersection and the number of cars that leave the intersection, you'd see that the same number of cars come in and go out over time. Now, we're assuming, of course, no car accidents or anything silly like that. So how can we apply these two things? Well, we're going to start with the simple series circuit, and then we'll work with the parallel. The series is actually the harder one, but we'll start with it anyway. So let's say we have a series circuit that involves, for the heck of it, 3 resistors. Let's make this one 10 ohms, this one 5 ohms, and this one 15 ohms. And we're going to put on a, let's put on a 15 volt battery. Just make the math work out a little bit easier. So if we use the current law, we can see that there are no junctions in this circuit. So what we can see is whatever the current that goes through this resistor, he hasn't had anywhere else to go by the time he reaches this resistor, or I1 equals I2 equals I3. The current everywhere in this circuit is the same. Basically, there's nowhere for the cars to go except for the one path, so if they're all moving around the circuit, then it's going to be, if you watch it over time, the same number of cars are going to pass by each point in the circuit. The voltage of the battery is shared by the electrical devices. That is Kirchhoff's voltage law. Again, if we imagine here we went up 15 flights of stairs, or up 15 stories in our building. We're going to come down some amount, some other amount, some other amount. Those V's, V1, V2, and V3 are not going to equal each other because those resistors are not the same value. They're all going to be different. So we have to figure out what those are. But what we do know is however much we went up when we went through the battery, we have to come down a total amount that's equal to that. So we have one equation here that says that the currents are all the same everywhere. We have a secondary equation that has 3 voltages in it. They're all different, and so we can't solve for them directly. But there is a trick. Those voltages can be expressed in terms of current according to Ohm's law. So by applying Ohm's law to the different resistors, then we can come up with 3 statements for the voltages. And what's important about those statements is they're all in terms of that common variable I, which means if we use them to replace V1, V2, and V3 in this equation, the equation's now only going to have one variable in it, and that means it's going to be solvable, which is good. This is just a matter of notation. It doesn't matter, remember, it doesn't matter what order you multiply things in, but in math we're used to seeing the number out in front of the variable as a coefficient. So we'll just rewrite this so we're a little bit more comfortable with it. And what that means then is that 15 is equal to 10i plus 5i plus 15i. And we have a bunch of i's. We have 10 i's, we have 5 i's, and we have 15 i's. So how many i's do we have total? That'd be 30 i's. Okay. We can divide both sides by 30, and we get a current for the circuit of 0.5 amperes. So what that means then is it doesn't matter where you look in the circuit entirely, the current is going to be 0.5 amps. Now if we use that, we can then come up with these individual voltage values. 0.5 times 10, or in this case 0.5 times 5 Or finally, 0.5 times 15. Let's not get those confused. So that would be 5 volts, that would be 2.5 volts, and that would be 7.5 volts. Now with that in hand, we can go back and look at our original idea in the first place. So what we're saying is we went up 15 stairs, and then we went back down 5 stairs, and back down 2.5 stairs, and back down 7.5 stairs. And so what we can see here is that 15 equals 15, and we've solved our circuit correctly. Parallel circuit's actually a little bit easier than that. In this case, whatever voltage we have in the battery is spread between however many branches we have in the circuit separately. So let's just do this. Let's make this a 20 ohm resistor, a 10 ohm resistor, and a, 5 ohm resistor. When we consider closed loops around this circuit, what we can see is for any closed loop, regardless of whether we look at that one, or this one, or the final one here, when we take a pathway from below the battery back through and back down to the battery, we end up only going through one resistor at a time. What that means is, for V1 for example, my 10 volts has to be equal to my V1. Similarly, for the red pathway, my 10 is equal to V2, and for my blue pathway, my 10 is equal to V3. So what that means is that the battery is almost powering these like 3 separate circuits. So the battery is providing all 10 volts to each circuit separately. Parallel circuits do not have to share their voltage. With this in hand, we can use Ohm's law at each individual resistor separately to come up with the current through those individual resistors. V1 equals I1 and R1, so if it's 10 equals I, and the resistance value for that first resistor is 20, we can come up with a current of 0.5 amps. For V2, I times the resistance value of 10, so 10 equals I10, which means our current simply equals 1 amp. And finally, for V3, I3R3, should call that I2. 10 equals I3 times 5, divide both sides by 5, and I3 equals 2 amps. Now what you see here is that each one of these paths has a totally different current. They have different currents because they let's call that I2 and let's call that I1, because they have different resistance values. It's almost like you have 3 separate circuits hooked up to the same battery. The current through the battery, I'm going to call that IB, has to supply all 3 of these currents according to Kirchhoff's current law. So the total IB has to be equal to the current from one plus the current from the other plus the current from the third, which I think was half plus 1 plus 2, or a total of 3.5 amps. What you can imagine then is, while a parallel circuit is nice because you can control the individual branches separately, they all get full voltage, there's lots of power to all those light bulbs, it's sure drawing a lot of current from your battery, which can be a big problem if you're using something like what's supposed to be a portable device like an iPod or something like that. So In general, the parallel circuit is the more common circuit to be used from a design perspective because you want to be able to turn things on and off separately. It does have the disadvantage of using a lot more power. Alright, let's look at this circuit here and let's see if we can use Kirchhoff's current and voltage laws to figure out what the unknown resistance is. We're just going to do a couple example problems like this, and then that'll be it for this video. So what we have on the far right hand side here is for what I'm going to call resistor 3. We know the resistance and the voltage right away. Whenever we have a pair of things at an individual spot in a circuit, we can always use that to find the third thing according to Ohm's law. V3 equals I3R3, and so we have a voltage of 4 and a current and a resistance of 10, and so divided by 10, I3 is going to work out to 0.4 amps. So that means we have 0.4 amps flowing through this part of the circuit. Now to come up with other values in this circuit, I'm going to do two things. So it doesn't particularly matter what order you do these things in, so I will pick somewhat arbitrarily. The first thing I'm going to do is I'm going to do a voltage loop that starts here, goes all the way to the back, down, and back across. What I'm going to see from this voltage loop is that I go up 10, down some unknown amount that I'm going to call, which is going to be V1, and then down 4 volts for that final resistor. What that means is that V1 is going to have a value of 6 volts. So this resistor is going to carry 6 volts. The second thing I'm going to look at is I'm going to look at a little circuit right here. Or you know what, I'll keep it simple. I'm going to go up, through, and down, and back. So now I'm just doing the inner circle. Here I'm going to go up 10, down the 6 volts that I just figured out from V1, plus down whatever I do in V2. 10 equals 6 plus V2. V2 is equal to 4 volts. What we can see here is the two resistors in parallel are experiencing the same voltage. What I'm calling resistor 2 R2 and R3 are in parallel. And we notice looking at that they have the same voltage. This, in fact, is always true for this kind of circuit. Well, this is true for any circuit. When the two resistors in parallel, they're going to experience the same voltage. Now, this has been a little bit of a roundabout, but now I'm going to focus on the V2 spot in the circuit. V2 equals I2 R2. I've got 4 volts, I2, and a resistance of 5 ohms. And so I2 is going to work out to be 0.8 amperes, which means the current in this branch is going to be 0.8 amperes. Now, the next thing I want to do is I want to focus on this junction right here. I've got a current coming out, I've got another current coming out, and I've got some current coming in. So by comparing those two current values, I should be able to figure out how much current is feeding it. I1 is coming into the circuit, I2 and I3 are coming out. Let's just take a look at this. I1 is coming in, I2 and I3 are coming out. So what that means then is if I2 is 0.8 amperes and I3 is 0.4 amperes, then I2 plus I3 must be 1.2 amperes. which means now at this location I know I have a V1 voltage of 6 volts and a I1 current of 1.2 amps, and all I'm missing is the resistance. V1 equals I1 R1, 6 equals 1.2 R1, and so R1 happens to work out to be 5 ohms. I sort of messed that up. I did the hard example first. Now I'm going to do a bit of an easier example second, but maybe that'll give you the courage to follow along and try your best to do this example with me. Remember what I said here. If we have two things at any one spot in the circuit, then we can use Ohm's law to solve for the third thing at that spot. So here we have a voltage of 5. We don't know our current, and we have a resistance of 10. So if we divide both sides by 10, we're going to see here that we have a current of 0.5 amperes. That's a 10. This is a simple series circuit. There's nowhere for the current to go. So if this current in this branch is 0.5 amps, then I know the current in this branch, and I know the current in this branch. Here, V equals, now I have 2, so I can find the third. V equals IR, which is going to be 0.5 times 5, which is 2.5 volts. And here, 7 times 0.5, 3.5 volts. Sorry, that's V equals IR. Now using a loop, if I start down here, go up here, cross here, down here, over here, then what I'm going to see is I'm going to go up some amount of voltage that's the voltage in the battery, and then I'm going to come down some voltage, I'll call V1, let's just call this one 1, and some other voltage, V2, and then down a third voltage, V3. Let's call this one V3. And based on the calculations I've just done, this one's 2.5, this one's 5, and this one's 3.5, for a total of 11. So what we're using to power this circuit is the rare but important 11 volt battery. That's a couple examples. There's more examples in the book. You could just keep doing examples like this over and over again. And as with most things, the best way to get better at solving these kinds of circuits is through practice, practice, practice. But I think that's a long enough video for right now.